In this video, we continue looking at aromatic compounds. In the last video, we started by looking at the example of benzene, dissecting why benzene meets the criteria for being aromatic, where we define an aromatic compound now, not as a compound that has a strong odor. Some aromatic compounds do have a strong odor, but that's definitely not the requirement for being aromatic. The requirement for being aromatic is exceptional stability. Stability that is above and beyond what we would anticipate for a typical conjugated triene system or conjugated system that is in a typical ring. So we classify the molecule as aromatic if it is exceptionally stable. And in talking about benzene as our specific example in the last video, we dissected that the reason why benzene has an exceptionally stable ring system, meaning that very, very, very few things disrupt those pi bonds in the ring. They can't undergo typical addition reactions or anything like that. They are exceptionally stable and non-reactive due to the fact that benzene meets several criteria. One of those, and what lays the platform for all of this, is that the ring system of benzene is a continuous system of sp2 hybridized atoms that allow that ring to be completely planar. Within that completely planar ring, due to the fact that it is completely planar and an sp2 system, there is an overlapping network of p orbitals. And those are what I highlight here as all these vertical p orbitals form a network or an overlapping system all the way around the ring of this molecule. And that is enabled by the fact that the atoms are planar and that they are all sp2. sp2 inherently is going to allow those p orbitals to be in place, and the fact that the system is planar allows those p orbitals to overlap. So the keys that we are deciphering or dissecting as being essential for benzene to be aromatic is that the ring is planar, the atoms are sp2, and those two things are going to allow for this system of overlapping p orbitals to be in place that is going to enable the energy of the system to be lowered due to the fact that there are exactly 6 pi electrons in that ring, and it just so happens that 6 pi electrons all fit into what are referred to as low energy bonding orbitals. If there were a different number of electrons in the pi bonds, say 8, instead of all of the electrons occupying low energy bonding orbitals, some of them would have to occupy high energy bonding orbitals or high energy non-bonding orbitals, and that would result in a dramatic decrease in the stability of the system. And so what we are going to look at in this unit is we are going to take this information that we have learned about benzene and create some rules that will allow us to look at any molecule and classify it as aromatic, meaning it's exceptionally stable, or alternatively, to classify it as the opposite of aromatic, which is referred to as antiaromatic, structures that are much less stable than would be predicted for standard alkene groups. So these antiaromatic compounds are exceptionally unstable. In fact, very, very difficult to synthesize because of that lack of stability. And so it's really important to be able to recognize whether a molecule that you are looking at is aromatic or antiaromatic, because from a practical standpoint, aromatic molecules are going to be much easier to synthesize and work with and use for practical applications such as drugs than antiaromatic compounds that are going to be very, very difficult to synthesize. And even if you were able to synthesize the compound, it would rapidly decompose and not be useful as a drug or things like that because of the fact that it is so unstable. Moreover, when we think about applying these concepts toward biological systems, what we find is that a large number of biological molecules, such as the building blocks of DNA, are composed upon aromatic skeletons. And that, from a logical perspective, makes sense because we think of DNA as being the long-term genetic transmission mode or way of storing genetic information. And we want that genetic code to be very stable and very readily transmissible from generation to generation. And so by building DNA upon an aromatic scaffold, that helps ensure that those molecules are relatively stable to be passed from generation to generation without large numbers of mutations. And so in looking at a molecule and classifying it as aromatic or anti-aromatic, what we are going to apply are the so-called Huckels rules. Huckels rules are referred to as this because the original person who described these rules and did a variety of experiments to validate these rules was named Huckels. So Huckels rules is a common term that is used to describe whether a molecule is aromatic or anti-aromatic. So let's take a look at Huckels rules, and then we will evaluate some representative molecules to assess whether they're aromatic or anti-aromatic based on Huckels rules, which are a set of rules that determine whether a molecule is aromatic or anti-aromatic or none of the above. All right, so taking a look at Huckels rules, which are useful when you are looking at a compound and trying to determine whether the compound is aromatic or anti-aromatic, meaning if the compound is aromatic, it's going to be much more stable than would be predicted for a typical conjugated molecule. If it's anti-aromatic, it's going to be much less stable and much more reactive than would be predicted for a typical alkene group in a conjugated molecule. And so in Huckels rules, rule number 1 is that for a compound to be aromatic, it absolutely has to be cyclic. So only rings can be aromatic. Within a particular molecule, if you see a ring system, it's possible that that ring system is extremely stable, meaning that ring system is aromatic. But if you're looking at a molecule and you don't see a ring system, or you're looking outside the ring system, that is definitely not aromatic. So for a compound to be aromatic, it has to absolutely be cyclic. In addition to it being cyclic, it must also be planar. And the reason why it must be planar all the way around that ring system is so that we can have those overlapping p orbitals. So that allows p orbital overlap that is essential for conferring the stability on the system. And then going along with that statement that the system has to be planar, so that we have those p orbitals and the p orbital overlap, in order for the system to be planar, we have to have sp2 hybridization available at each atom of the ring. So there has to be an sp2 hybrid possible at each atom within the ring. And what we mean when we say an sp2 hybrid is possible at each atom in the ring, based on the way the structure is originally drawn, you might look at it and you might say, oh, that particular oxygen in the ring is not sp2 hybridized, it's sp3. Well, when we say that an sp2 hybrid is possible, what we mean is that you can draw a resonance structure where you can show that that particular oxygen can adopt an sp2 hybridization. So when we say sp2 hybrid is possible, that means that at least one resonance structure shows that particular atom as sp2. That doesn't mean that every single atom has to be sp2 in a particular resonance structure. It just means that you can draw one resonance structure where, as you look at a particular atom, you would say, yes, that particular atom is sp2 in at least one of the resonance structures that I can draw for it. There might be some other atom in that particular resonance structure that's sp3, but ultimately, when you are looking at the different resonance structures that are possible, if you look at each individual atom, you can go around and say, okay, there's a resonance structure that has this particular atom, sp2, in at least one of the resonance structures. There's another resonance structure that has this other atom, sp2, in at least one of the resonance structures. And make sure that each and every atom in at least one resonance structure, that one atom can be sp2 at some point in looking at the resonance possibilities. And then finally, as criteria 4 here, for a molecule to be aromatic, it has to meet all three of the criteria above. In addition, it must have a so-called Huckel number of pi electrons in the cyclic 2p orbitals. So we need to dissect this a little bit further. So when we say it must have a Huckel number, what do we mean when we say a Huckel number? The Huckel number of pi electrons is going to be the perfect number of electrons to occupy all of the low energy bonding orbitals. And this is what's going to be one of the main things that confers this excellent stability on the system, is that all of the low energy bonding orbitals are occupied and none of the high energy anti-bonding orbitals are occupied. And that is going to be true if we have a specific number of pi electrons occupying the system. If there's a specific number referred to as the Huckel number, that will mean that all the low energy bonding orbitals are occupied and none of the high energy bonding orbitals are occupied. So what is a Huckel number? The Huckel number is equal to 4n plus 2, where n is equal to an integer, and that integer can be as little as 0. And we refer to Huckel numbers as any number of pi electrons within that ring that meet this criteria. So specific Huckel numbers, where we fill in n as an integer, starting with 0, 4 times 0 plus 2 would be 2. So in other words, if we look at a ring and we see a grand total of 2 pi electrons in that ring, that indicates that the molecule is aromatic, as long as it also meets these first 3 criteria. Going onward, if we set n as our next integer up, which would be 1, 4 times 1 plus 2 would be 4 plus 2, which is 6, is another Huckel number. By the way, 6 was the number of pi electrons that we saw in benzene, so this is so far corresponding to what we observe for benzene, as expected, since we know benzene is very, very stable and hence aromatic. Next Huckel number on the list, if we set n equal to 2, 4 times 2 is 8, plus 2 is 10. So 10 is another Huckel number. If you see 10 pi electrons in that cyclic system, that indicates that the molecule is aromatic. If we take and set this as n equals 3, 4 times 3 is 12, plus 2 is 14. So our next Huckel number is 14. So based on this lineup here of Huckel numbers, we could continue working upward here and go to even higher Huckel numbers. Sky's the limit there. But the idea is that anytime the number of pi electrons in that ring system is 2, 6, 10, 14, and onward, meeting this template of 4n plus 2, where n is any integer, if you count a number of pi electrons in the ring that corresponds to any of these numbers on up the line, that is going to correspond to an aromatic molecule, as long as all 4 of these criteria are met. And generally, when people are analyzing these structures and evaluating whether they're aromatic or not, people look typically at the first 3 factors first, because if those aren't fulfilled, then there's no point in looking for a Huckel number. So these compounds are going to be classified as aromatic. What about compounds that instead of having a grand total of 2 pi electrons or 6 pi electrons, what if it had instead 4 pi electrons? That doesn't fit this template of 4n plus 2. There's no way to make 4n plus 2 equal to 4 with n being an integer. So what would the case be in that situation if you had a molecule that had 4 pi electrons? Well, the Huckel rules continue, because in some cases, the number of pi electrons is going to be a number that will force some of those pi electrons into the high energy anti-bonding orbitals. So we can add an addendum here where instead of looking at the criteria for a compound to be aromatic, we can ask what's going to make the compound anti-aromatic, meaning extremely unstable. So it's the opposite of an aromatic molecule. These compounds are less stable than would be expected for a typical alkene. They're going to be anti-aromatic if criteria 1 through 3 are met above. So in other words, for a compound to be antiaromatic, has to be cyclic, has to be planar, has to have sp2 hybridized atoms possible at each position in the ring. And then additionally, the way that aromatic and antiaromatic compounds diverge is that at criteria 4 here, rather than having a total of 4n plus 2 pi electrons, where n is an integer, and so your number of pi electrons is 2, 6, 10, or 14, the number of pi electrons is equal to, rather than 4n plus 2, it is equal to 4n, where n is an integer. And so, dissecting that, we can say a compound will be antiaromatic if it meets criteria 1 through 3, and it has the following numbers of pi electrons. So if the pi electrons are equal to 4 times 1 would be 4. Going back to this business about n being an integer, if n is equal to 2, it'd be 4 times 2, which means 8. If n is equal to 3, 4 times 3 is 12. If n is equal to 4, 4 times 4 is 16, and so on and so forth. And so what we see is this pattern of aromaticity versus anti-aromaticity, where if we have up top here 2, 6, 10, 14, and so on, pi electrons, we classify the molecule as being aromatic. On the other hand, if rather than having 2, 6, 10, 14, etc. pi electrons that meet this 4n plus 2 criteria, if instead the number of pi electrons meets the criteria of fitting the paradigm of 4n, the compound will be antiaromatic, meaning that the number of pi electrons works out to 4, 8, 12, 16, etc. And so you can count the number of pi electrons in the ring system and compare it to these Huckel numbers for aromaticity versus antiaromaticity to determine what type of molecule you are looking at. You'll notice all of these encompass the entire range of even numbers from 2, 4, 6, 8, 10, 12, 14, 16, and so on and so forth, all the way to the sky's the limit. And the number of electrons in these cyclic systems will always end up being even numbers because of the fact that these pi bonds are spanning two atoms. So you end up with a total of 2 electrons in these continuous sp2 systems. So you won't run into a situation where you have an odd number of electrons in these types of aromatic or anti-aromatic systems. Will always be an even number, and by comparing how many of those pi electrons there are to match up with either the 4n plus 2 value of 2, 6, 10, or 14 pi electrons, or the antiaromatic value of 4, 8, 12, 16, etc. pi electrons, that will tell you whether a molecule is aromatic or antiaromatic. So this is really great information to commit to memory and or keep handy, is this Huckel formula for determining whether a molecule is aromatic or anti-aromatic. And then the third scenario that we can think about is, so far we've talked about what about for an aromatic molecule, what are the criteria for an anti-aromatic molecule, and then the third situation would be none of the above, because the vast majority of molecules that we will run into are neither aromatic nor anti-aromatic. And so the third option is any compound that doesn't fit all of these criteria is neither. So any compound not fitting all criteria is neither anti-aromatic nor aromatic. So if you look at a ring system and you see that there is some position of the ring where the atom simply can't be sp2, you can immediately say the compound is neither aromatic nor anti-aromatic. It's just none of the above. It does not fit those criteria. So those are the 3 possibilities for every molecule in the universe, is that the molecule is either aromatic, anti-aromatic, or none of the above. And the only way a compound can be aromatic is if it fits all of these criteria 1 through 4. The only way it can be anti-aromatic is if it fits criteria 1 through 3, and then at criteria number 4, it has this 4n number of pi electrons in the ring. So I've zoomed out a bit on our rules for determining aromaticity versus anti-aromaticity. so that we can take a look at the example problems on the right side of the screen in blue. I strongly encourage you to hit the pause button, try to work through these on your own based on the rules that we have here at the left, and then hit play to see how you did in determining whether you have mastered these Huckels rules or not. So in the first example, we have a 4-membered ring here, which we could refer to as 4-aniline. We could also refer to it as cyclobuta-1,3-diene as an alternative name to that. So in determining whether this is aromatic, antiaromatic, or neither, first criteria first on our list over here at the left, the molecule has to be a ring. Yep, definitely a ring. So we're good to go there. It has to be planar, and for it to be planar, what that generally means is that each of the atoms in the ring is able to adopt an sp2 hybridized electrons in at least one of the resonance structures. So in the case of this molecule, as it is written all the way around, it is indeed sp2 at every single carbon atom, because each carbon atom, as it's written right now, has 3 regions of electron density. And then finally, to determine whether the molecule is aromatic or antiaromatic, since we filled the first 3 criteria, we have to look at point number 4 here and determine the number of pi electrons in those cyclic 2p orbitals and whether it fits the Huckel numbers for aromaticity, meaning there are a total of 4, 2, 6, 10, 14, etc. electrons in those pi bonds, or whether it is antiaromatic, meaning that the number of electrons there is 4, 8, 12, 16, and so on. So taking a look at this, at each position where there is a pi electron, there's a pi electron here, 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 and here. So there's a total of 4 pi electrons because each pi bond contributes 2 pi electrons. And so therefore, with 2 pi bonds in this molecule, that means we have a grand total of 4 pi electrons to consider here. When we have 4 pi electrons, matching that up with our Huckel numbers for aromaticity or our Huckel numbers for antiaromaticity, this molecule of 4 pi electrons is going to be antiaromatic because of the fact that that 4 pi electrons fits this 4n rule, where n is an integer. In this case, if n is equal to 1, then the total number of pi electrons equals 4, which fits that criteria for antiaromatic. So 4 pi electrons is going to be antiaromatic. Coming on to the next example problem, right here, we have our molecule that we could refer to as cyclopenta-1,3-diene. And in this molecule, we take a look at it, going through our criteria here. The molecule is cyclic, so we're good to go there. Planar, and linked with that planar criteria is that each atom has an sp2 hybrid possible on every single atom that's in the ring. So as I look at this, our pi bonded carbons all the way through here where I'm highlighted, those are all sp2 right now. But we have an sp3 carbon right here because that carbon is not part of a carbon-carbon double bond, so that would be a CH2 group there. And as a CH2 group, that is going to be an sp3 carbon atom right there. And so in order to determine whether it's possible for this molecule to be aromatic or not, we have to ask, is there a way to draw a resonance structure that would allow that sp3 carbon atom to become sp2? And thinking about that, there's no way to accomplish that without going over the octet rule. And we can never go over the octet rule because if we tried to move a pi bond over to here, to make a pi bond right here, we would go over the octet for that carbon. And so there's no way to make that carbon participate in a carbon-carbon double bond and be sp2 hybridized due to the fact that we're already at the octet there and there's no way to move electrons around to enable that carbon to be sp2 without going over the octet. And so since it is not possible in this structure to create an sp2 carbon at that position by drawing a resonance structure, that means that by criteria number 3 on our list over here at the left, the molecule cannot be aromatic or antiaromatic. So I'm going to put this one down as neither. It is going to behave like a standard, typical conjugated diene. It is not going to be exceptionally stable or exceptionally unstable, meaning it is not aromatic or anti-aromatic. It's just, it is what it is. All right, so on to the next one. This particular molecule here is named as furan. If we're looking for the typical name that is used to refer to this molecule, where we have an oxygen heterocyclic compound with our two double bonds here and here. So in thinking about whether furan is going to be aromatic, anti-aromatic, or neither, going through our criteria, is the molecule cyclic? Yes. Is it planar? And by planar, we mean that the molecule could become planar by having an sp2 hybrid atom possible at each ring atom and at least one of the resonance structures. So we have to ask here, since initially in the way this is drawn, the oxygen, being that it has two sets of lone pair electrons on it, that means there's 4 regions of electron density in total. This oxygen, as we've drawn it right here, is sp3 at the structure that we have drawn. But by resonance, we have to ask, can that oxygen adopt an sp2 hybrid? And so in order to determine that, what we do is we try to draw a second resonance structure. And we say, okay, is there a way to make this oxygen that's sp3 into an sp2 oxygen, meaning that the oxygen only has 3 regions of electron density in total instead of 4. So we could take the lone pair electrons, we can move those over to right here to make an oxygen-carbon double bond. And in doing that, we have to move these pi electrons somewhere to avoid going with that tight. We can move those right onto that carbon there. And in so doing, I'll go ahead and draw this out here. We would still have one set of lone pair electrons on the oxygen. Then we have a lone pair over here on the carbon, negative formal charge. And what we would see is that now this oxygen is sp2 rather than sp3, because now the oxygen only has 3 regions of electrons. It has the double bond going to a carbon, single bond going to a carbon, and the lone pair, meaning it's sp2. Now, granted, in doing that, what we did was we also, as a result, created a carbon over here, which would now be sp3 because it has 3 bonds to other atoms plus the lone pair of electrons, meaning 4 regions of electron density in total, meaning sp3. But that's okay because we just have to set this up so that in resonance structures, we have at least one resonance structure where we can show that each of the atoms is sp2. And so it's okay that by making this oxygen sp2, we made some other atom in the ring sp3, because in the original structure, that carbon atom was sp2. So we just have to be able to look at the full set of resonance structure and say, okay, for each individual atom, there is some resonance structure where that particular atom is sp2, and things will work out to meet this criteria of having an sp2 hybrid possible. So for furan, there is an sp2 hybrid possible at each and every atom in the ring. And so now what we need to do is take our favorite resonance structure, whichever one that is, and we are going to count the number of electrons that will occupy those cyclic 2p orbitals. So in order to do this, I'm going to erase our resonance arrows here so that we can take a closer look at the electron arrangements. Now I've zoomed into our structure here and gotten rid of those electron pushing arrows so that we can look at it a bit more closely. And we're going to go in and count the number of 2p electrons that would count toward this Huckel number for aromaticity or the Huckel number for anti-aromaticity. So any pi bonds count for 2 electrons. So I'm going to highlight pi bond here and pi bond there. And I'm just going to annotate here that each of those will contribute 2 electrons. So we're up to a total of 4 electrons so far. Then we look at the oxygen atom. And you might be saying to yourself, what do we do with those oxygen electrons? Because we have 2 sets of lone pairs, and we showed that one set of those lone pairs could participate in forming a pi bond. And so we do count that one set of lone pairs that can participate in forming a pi bond, because it will be possible for that set of electrons to occupy the 2p orbital and come into that perfect vertical alignment for the electron delocalization in this system. And so we count one of those sets of lone pair electrons in our count here, because we could take that set of lone pair electrons and then this other resonance structure show it being converted into a pi bond. So even though it's not shown as a pi bond right here, we still count it because by resonance, it could be shown as that pi bond instead. The other set of lone pair electrons we do not count, because that other set we could not show as participating in pi bonding. It's either one or the other that can participate in pi bonding at a time. It's not both that can participate. And so therefore, we only count one of the two because it would only be one of the two, in other words, that could occupy that vertical 2p orbital. Both sets could not simultaneously occupy that orbital because the orbital would be overfilled. So we can count those 2 electrons right here on the oxygen. And that is going to be true in any situation where you have an atom that has 2 sets of lone pair electrons, and you can show that one of those sets can participate in resonance. You will count that in that count of 2p electrons that contribute toward aromaticity or antiaromaticity. So therefore, based on this count, our total number of our 2p or pi electrons is equal to 6. We had a pair from the pi bond here, a pair from the pi bond here, and 2 more from these lone pair electrons, which we were able to show could participate in resonance. So we can count those as an additional 2 electrons there. So that gives us a grand total of 6. Looking back at our Huckel numbers for aromatic or antiaromatic, we see that 6 fits the definition of aromatic. And so therefore, I'm going to go ahead and label this compound as aromatic. And then the conclusion that we can make, based on looking at all 3 of these compounds that we just assigned as aromatic, antiaromatic, or neither, is that the structure we've listed down here at the bottom, furan, is going to be the most stable of all 3 of those compounds because it's the only one that meets the criteria for aromaticity. On the other hand, the least stable of the compounds will be this 4-membered ring that we describe as being antiaromatic. And then finally, right in the middle of the road, is going to be this conjugated diene that we have in the middle of the screen because it is neither aromatic nor antiaromatic, meaning that it's not exceptionally stable, nor is it exceptionally unstable. So this concept of being able to recognize whether compounds are aromatic or antiaromatic is very fundamental, both toward applications in organic chemistry, such as recognizing whether a molecule should be readily synthesizable or not. It's also useful in the spectrum of evaluating biological molecules and considering how stable or unstable they should be in the natural world. And also from a practical standpoint, for many of you, this concept of aromaticity very commonly comes up on standardized tests such as the MCAT, where they will give you a structure and ask, is this aromatic, antiaromatic, or neither? And remembering these guidelines will be really useful for answering those types of questions.